lecture first. All right, so we're going to attack this problem together. All right, so I hope you probably have tried this a little bit. So key concept, once again, all right, we understand that this whole thing, this cyclic process right here is trying to represent a heat engine, okay? So that means what we are trying to get to sort of like calculate everything is just to get to all the information about the heat flow, the work done, and everything else, which of course is going to be running within those three parameters in the first law of thermodynamics. That I think we have been writing this equation like a million times already. Okay. Already. So that is good. So now, so what we are trying to do is start from each segment, just like what we did in the last latest exercise. Okay, so let's start from 1 to 2. And let's see what kind of information we can extract from this. All right, we have been doing this quite a lot of time, so let's dive into it. So the question that they want is simply just asking about the efficiency of this engine. Okay, so that is just the how can I say it, like the way that you can describe like how well this engine is going to run. Okay, so let's start from 1 to 2. Everyone's probably comfortable at this point. It's obvious right away. There's no work done because volume does not change. Cool. All right. Second thing, of course, first law of thermodynamics now is going to reduce down to just this because W is gone. Plus, you have already learned that U is 3/2 nRT. So delta U is going to be 3/2 nR delta T. Perfect. Plus, you have written this in terms of the N C sub V delta T if you want to. Okay, so this means you should be able to calculate all three terms. W is gone, is 0. Delta U is equal to Q is equal to NCV delta T. Okay, sounds good. Keep going. So it's going to be 3/2 nR T final, T at 2, minus T initial, T at 1. Very good. But of course, you don't know the temperature, but that's all right. Because nRT, according to equation of state, that is just a product between pressure and volume. Just keep going. It's going to be 3/2 P2V2 minus P1V1. All right, you guys, so far so good? All right, and that's it. Just read off from the scale in the PV diagram. P at 2, V at 2 is right here. So it's going to be 2P0, V0. So it's 2P0, V0 right there. And at position number 1 is P0, V0 right there. And that's it. So it's 3/2 P0, V0. And it's positive. So it's good. It's sort of like in sync with what we have been doing. It's positive because heat must be entering. So I should be able to draw arrow like this. And let me name this Q12, shall we? All right, and then I can erase the rest. All right, you guys already got that information down. So just make this a little bit less messy right there. So that means during the segment 1 to 2, heat enter the system. When I say enter, so I try to put the arrow into the internal area of the cyclic process. Yeah, but that is just sort of like a convention or sort of like, I don't know, people just doing this. So we just keep doing it. All right, so the arrow that enter into the internal area, that is the heat flow into the system. However, it's coincide with what we have already been studying. You know that point number 1 must be lying on an isotherm. Point number 2 must be also on an isotherm. Right? I mean, 2 and 4 might not be on the same. I'm just drawing. But just considering 1 and 2, you see that going from 1 to 2, you're jumping from a lower isotherm to a higher one. And that makes sense. When you move to a higher temperature, delta U is supposed to be positive. You are increasing in internal energy. So check. Very good. Heat flow into the system to increase the internal energy without performing any work. the volume does not change. Isn't that good? All right, I suppose you have an effect here, but haven't set it up, so that's what it is. Oh, wait, the sound is not going to be good. Oh, it's kind of far away with sound. All right, I haven't plugged it in yet. Oh, my bad, my bad. Okay, let me plug it in first. Oh, shoot. All right, I hope it will sound better now. You don't feel anything? Is it better? I hope. Microphone. Let's pick the USB. Hello, test. Is it better? Oh, I hope it's better. All right. Yes. Okay. Thank you. Sorry about that. Maybe I'm just rushing too much. All right, you guys got this? This part is good. So that's what we have been doing like forever, I think. All right. It's been 3 weeks already. All right. Try again. Shall we? Go from 2 to 3. I think at this point, you should be sort of like, okay, Dan, it's not difficult anymore because we should be able to write down all 3 terms. Let's change the color a bit here. All right, go from 2 to 3 right there. All right, everyone can see that it's an isobaric process. Good. So with the isobaric, one thing that you know right away is W is going to be, it's always area under the curve. But for the isobaric process, the area is so easy to calculate because it's just a rectangular area right there. There. Let me highlight this in green. That's the area under the 2, 3 segments right there, the green curve. So it's going to be P delta V. Yeah, it's just a width times the height. The height, which is just the pressure right here, is the whole thing there. Okay, you guys with me? So the height is 2P naught. The delta V is going to be this. That is your delta V. That's the width. But then we always take care of the sign. That means you're going from where to where. So it's going to be final volume minus initial volume. But you can see from 2 to 3, it's expanding because the final volume at 3 is going to be larger than at 2. So you're going to get a positive number out of this. So it's going to be 2 V naught minus V naught. You guys with me? All right, very good. And that's it. So I get 2 P naught V naught. That's the work done during the 2 to 3 segments. What else do you know? Well, Ajahn, actually, I can do everything else because if you want to jump right into the calculation of the heats, heat 2, 3 is going to be what, guys? N C sub P delta T. You guys with me? You can jump right ahead into it. And that is going to be 5/2 NR delta T. For those of you that don't want to jump right into this expression, is just going to be the delta U plus W. Just move W to the other side, leave the Q behind on the left-hand side, and that gives you 3/2 NR delta T plus P delta V. And the sum of these two will get you back 5/2. We have done this 3 times already. I think this is the 4th time we're doing this. But I think you guys sort of like, okay, I have seen that before. All right, so I can keep going. 5/2 nRT. So it's going to be nRT final, which is temperature at 3, subtract temperature at 2. Very good. And once again, even though we don't know we don't know temperature at 0.3, but nRT is just going to be P times V again. We use the same trick. Okay, use the state equation of states to help. All right, so keep going, guys. So whatever route you're going to take, at the end, you're going to get 5/2 P3V3 minus P2V2. Yes. Very good. And that's it. You can read the values from the 2 axes P and V. All right. At point number 3, it's 2P naught, 2V naught. So it's going to be 5
have 2 P naught times 2 V naught. Okay, now subtract out what is going on at point number 2. The pressure is 2 P naught. The volume is only 1 V naught right there. There you go. All right, and that it's 4 minus 2 is 2. 2 cancel with 2, so it's 5 P naught V naught. Very good. And once again, the final answer that you get during the 2-3 segments is positive. So what does it mean? It means during this process, so let me erase those stuff out. Get rid of these. So it's saying that during this process, the heat is flow into the system as well. It's positive heat. Okay, very good. All right. And still, if you really want to just talk about the delta U, the delta U is also positive because point number 3 is still at a higher temperature. Draw another isotherm right there if you want to. Okay, but my point here is, see, so now you are able to calculate all 3 terms in the first law of thermodynamics. You know how to do the work done. That's the easiest because it's just an area under the curve. You know how to do the delta U because the formula is fixed. It's 3/2 N R delta T. And then from these 2 terms allow you to calculate the heat involved during that process. And once you get all 3, everything is going to be in your hands. Good. All right, not too bad. All right, from the look of it, but Ajahn, I know how to do the rest. You can go 3 to 4 and 4 to 1 with the same way of doing this. And 3 to 4 is going to be easy because it's a constant volume process. 4 to 1 is going to be another isobaric process. Yes. All right. That's one way of doing it. You can check if you want to. However, I would like to give you a clue. Well, it's not even a clue. It's going to give you a solution. I have another way to approach this final conclusion about the efficiency of this engine. The way to do that is, can you guess? I don't need to do section 3, 4, and 4.1 anymore, as long as your answer is about the efficiency. Why? Because the efficiency is going to be the amount of work done divided by the Q hot, right? You guys with me? Okay, remember this, right? And the Q hot is the heat that actually entered the system. In contrast to the Q cold, is the one that you discard out to the environment. So over here, can you guess what is going to happen during the segment 3, 4, and 4.1? What do you think? So think about this. 1 to 2, you jumping up, right? It's a constant volume process, but it's increasing in pressure. Of course, but Ajahn, heat flow in, temperature rises, no big deal. 3 to 4 is just a reverse of that. So I can guess without any calculation that 3, 4, the heat will be leaving the system. But of course, the amounts probably will be different. But the point is there will be heat flowing out from the system during 3 to 4 because it's an inverse, it's a reverse process from 1 to 2. Okay, 1 to 2 is up, 3 to 4 is down. Same idea with the 2, 3, and 4.1. Because 4.1 is a compression of the gas, even though it happens at the lower pressure. But the idea is during this process, there will be heat leaking out. Because this is just a reverse, it's not a reverse process, but it's a process that go in the opposite direction to the 2, 3 segments. Cool? All right. And the reason that it said I don't need to do the Q3, 4 and Q4, 1. Oh, sorry, it's 3, 4, 3, 4. I can see that now. All right. It's not, you don't need to do the calculation of those 2 Qs because I can figure out W right now. Can you? The Q hot is done. When I say it's done, because the Q hot is already known to be Q1. Oh, don't use the arrow at this point. You guys got confused. This one is just going to be equal to Q12 plus Q 2, 3. You guys with me? Because Q hot is the heat that is flowing into the system. And from the diagram, you can see that there are only 2 segments that the heat flow into the system is Q12 and Q23. So that means you already got the denominator part, Q hot. That's good. So the only thing left is if you can figure out the work done, then you're pretty much done. Okay. And you guys sort of like vaguely remember, I hope, how can you figure out the work done in the cyclic process? Yeah, the sound effect's supposed to be in right now, but I don't have it yet. It's just like, yes, correct. Whatever you're thinking is correct. It's going to be the area enclosed by this process. Remember that? All right, you don't need to remember actually. It's just the area under the curve on the way to the expansion, erase out the area under the curve on the way back. So the leftover area is just area within that internal part of the process. So this is your W right there. So it's just a rectangular shape. Okay, and once again, you can do that. It's just the width times the height. Okay, so that means it's just P naught, V naught. Can you see that? Okay, the width is P naught. I mean, the height is P naught. The width is V naught. And that's it, guys. I got my answer. So efficiency is P naught, V naught over Q12. We already got it to be 3/2 P naught, V naught plus Q23. We already got to be 5 P naught, V naught. And as you can see, those P naught, V naught will cancel them all out because we know the efficiency is just a number, right? It's unitless. And that is going to be 1 over something, 13 over 2. So the answer is going to be 2/13. Done. Voila. Sounds good, looks good, feels good, I guess. All right, but for those of, sorry, for those of you that really want to check, like, well, Ajahn, is this true? Is this real? You can actually verify that if you go through the whole full calculation of the heat Q34 and the heat Q41, and then you do the difference, you can see that, you will see that the sum of these two, subtract out the sum of these two, will be equal to W. You guys with me? Because the heat in subtract the heat that is flowing out from the conservation of energy, it must be the work done by the engine. That's it. That's the whole point. Okay, what if the cycle is reversed? Okay, that's a very good question. So what we are learning over here, you start to see that the cycle is clockwise. When you have a clockwise process like this, you now verified by doing the full calculation that the W is positive. So that means each cycle, you gain some work done from the system. So that means this is exactly the heat engine, right? Here. Where's that? Here. This is the heat engine that we started out. That it's a heat flow in, subtract the heat flowing out. The leftover is the work done by the engine. But if things run in reverse, that's going to be exactly the heat pump. Because if that cycle go counterclockwise, that means the W is going to be negative. So it means you have to supply work to the system. Okay. And because the arrows and everything that we have done is going to be reversed. So it means you're trying to pull the heat from the colder part and dump it out up there at the higher temperature. So if this were to go counterclockwise, all of the arrows will be opposites, and that is going to be the heat pump. Very good. And that's a very good question, actually. So that's give you a conclusion that every time that you have a cyclic process that runs in the clockwise direction, that is the heat engine. And if you have the cyclic process that run counterclockwise. That is the heat pump. Very good. Got that? All right. I hope this is good. Any other questions? Very good questions. Thank you. All right. Yeah, the effect. Okay, I don't hear it though. My setup is sort of like not in place. All right, cool. So I think that is the grand conclusion of what the first law of thermodynamics and the application is. That's it, guys. That is done officially. For the rest of the lecture, I would like to introduce to you I think we almost got everything. The only leftover is the second law of thermodynamics. So once again, just want to recap all the laws in thermodynamics, even though we didn't really do in detail, but at least you have heard all of them. The zeroth law is just the thermal equilibrium, right? So it's just trying to explain about the thermal contact and what does it mean by thermal equilibrium. So when you talk about the zeroth law, you can think of it like a thermometer. If you dip a thermometer in one and it reads 36, you dip into another one is 36. So you guarantee that those two objects, once they are put in thermal contact, they are in equilibrium. So that's just a zeroth law. The first law of thermodynamics, that's what we have been doing crazily, like overly, maybe too much already. But in the nutshell, the first law of thermodynamics is just a conservation of energy. But this time, it's distinguished itself from just the conservation of energy in Newtonian physics, in the sense that you include the thermal property into it. So you allow the energy to exchange due to temperature difference. Cool. All right. So that, I mean, that's kind of nice and everything. But then at the time that we tried to introduce to you the Carnot engine, we were talking about the reversibility. And we discussed about the reversibility, that the first law of thermodynamics doesn't give you anything about the directions. So, and that links to the second law of thermodynamics. It's about how the process should go. There seems to be only single direction that the system will evolve. Okay. And that's follow the second law of thermodynamics. All right. And that's what the rest of the lecture will be. And the third law, just to conclude them all, the third law of thermodynamics, just saying that the 0 Kelvin, the absolute zero, is an unattainable temperature. You cannot reach 0K. It's impossible. That is just the third law of thermodynamics. And that's it. You have heard them all. You have 3 laws of thermodynamics plus the 0th law. So actually there are 4, but that's what it is. Okay. And you have sort of like looked into first law like in full details along with their applications. All right, so that's a comment here. Laws are good, but I want to cool the water by dropping some ice cube without thinking much. Yeah, you don't have to think about it, of course, as long as you're not trying to engineer anything. So just enjoy a cup of hot coffee or I don't know, cold drink, and then just be done with. Yeah, I think it's fine. I haven't thought about thermodynamics every time I eat my noodles or anything either. All right. Okay, very good, guys. So let's talk about what is it, the second law of thermodynamics. And I think you guys probably have heard of this. It's going to have a main character in this law, and it's entropy. And this is the crazy part, because entropy is a very annoying concept. The reason it's annoying is because, first of all, it's so hard to imagine what is going on. The second of all, it's sort of like something is with you, but you are not really using it much, because it's like a law that you will see. It's not like a equality, like this has to be equal to that, but it seems to give you a trend, or it gives you something that has to happen. So most of the time, it might not feel exact. So the calculation sometimes is kind of like, it's qualitative somehow. But I mean, you can do quantitative calculation, of course, once we define what does the entropy mean. So let's take a look at this quickly. I don't know, have you heard of this one before, but the main words that people throw into explaining the entropy is the disorder. I don't know, have you heard of this before? But even this, I think I got this one from the textbook. It just say entropy is a measure of disorder in the system. Wow, but I don't think this is a very good explanation, and it's kind of like misleading somehow, right? So hear me out a little bit. Anyway, let's stick with that. The idea is not bad, but it might not give you a good intuitive sense of what the entropy is about. So let's talk about this from the textbook perspective first. So heat only flows in the direction that increases disorder or randomness of the system. So here we go. And again, one more word, the randomness. Oh, crazy. So it seems like everyone probably agree with me that the system that looks disorder, that means it has a higher degree of randomness. Does that make sense? Yeah, it looks fine. That's agreeable. So that should be okay.
Okay.
Right. Now, how can we define it quantitatively? So let's take a look at this. We go back to our gas system one more time. So, and take a look at a simple case in an isothermal process. So that means we're going to keep our temperature fixed. Very good. With that, delta U will be gone. So there won't be any change in the internal energy. And the first law of thermodynamics say the delta U equal to Q minus W, and it's going to be 0. And that means Q is going to be equal to W. And you know further that the W is just the area under the curve. We did the calculus of this, and we know it's the nRT log V final minus V initial on and on, if you want to find the area under the curve, correct? However, what we're going to do is we're just going to look at the differential change at this point. So what is the heat flow? You say, well, okay, it's just going to be the work done. And the work done is just PdV, pressure times the volume change, a tiny change. But then we can represent P as an nRT over V. And this is how we arrive at the point that, okay, if you want to find the whole work done, you just integrate this expression, correct? That's why we got the log of V as a final result. But at this point, we're going to take a break right here. It's just like, okay, stop. Let's think about this. And let's focus on this term right here. Whoa. It turns out if I just focus on this one, I can move nRT to the left. So it looked like this. And believe it or not, actually this terms already imply disorderness. Wow. The change of the disorder. Wow. So what does it mean? Think about this. So now you have a volume. The gas is in this volume, but suddenly the volume changed. Yeah, dV. And let's say it's a positive change. So that means I have more volume. So if I am one of those molecules running around, and then suddenly, well, hey, I found more volume, I can sort of spend time in that extra volume. So I can go crazy more. I don't know. I always use an analogy. Think about like you have like a playground for kids to play. But then you think about it, suddenly the area of the playgrounds doubles. So the kids will just like, oh, crazy. And then the parents just get more headache, right? So that level of headaches, that is the randomness of the kids running around in the playground, something like that. So the idea is when you have more volume for the gas to travel, that means you have more ways for the gas to travel. And that means the disorderness is increased. Make sense? Sort of, yeah. But the point of this one is it's a give you a very quick link to the term on the right. The only term that's still a variable, sort of something that can still change, is this ratio right here. Is the heat involved in this system within that temperature? The N is fixed, the R is just a constant, and that's why physicists look at this ratio, the heat and the temperature, and that's entropy. It's entropy, guys. And it turns out for those physicists that came up with the name, they try to have a name that's gonna rhyme, or it might not be a rhyme, but it's gonna sound very close to energy, because they was thinking that this term is actually as important as energy. So they come up with the entropy. But it turns out we haven't calculated entropy much in our lives somehow. Yeah. All right. So, but why do we care so much about this? Because it turns out it has the same property as energy. It's path independence, guys. We love it. Seriously. All right. We love it because every time that you have a path independent variable or quantity, that means you don't need to care about the path at all.
Okay.
So just like energy, we don't care. You give me the starting position, final position, you're done. Same thing with this. So it means you just give me this initial state, final state. I can tell you what the entropy is going to change right away. So that's good. All right. So the only sort of like the detail, the fine detail of this calculation is, well, Ajahn, wait a second. Even though you said it's just a ratio between the heat and the temperature, but we already discussed this before, that this heat itself is path independent, path dependent. So that's going to be bad though, Ajahn, because it seems like you can go as crazy as you want. You can put any heat to it. You can extract any heat out of it. Isn't that going to be bad for the entropy definition? Well, yeah, you're right. It shouldn't be any heat. It turns out the big requirements of this expression is your heat calculation must be calculated from a reversible process, because we already discussed, if you have a heat in the process that is irreversible, that heat is a useless heat. It's like a lost heat. And once the heat is lost, I mean, you can make loss as much as you want. I mean, yeah, you can lose in so many ways. So that's hard to keep track. So that's why you're only going to take care of the heats that you can account it for. You want to account for those heats that is still within your system. It's reversible. At least when it's go, you know it can come back. It's not like go and gone. At least it's gone a little bit, but I mean, eventually it's going to come back. So that's why we have to put the subscript R into it. And that's the way that you can calculate the entropy change, by looking at the heat from a reversible process over the temperature. But the nice thing about this one is you can pick any process as long as it's a reversible process. So what does it mean, Ajahn? It means if you can write a PV diagram, remember the PV diagram give you from initial point to another final point, it's reversible. And we talked about, we do things slowly enough, everything is in equilibrium all the time. So as long as you can plot a point in the PV diagram, and then you can trace a curve, that curve is reversible. And once you have that curve, you can calculate the heats. But the good thing about this entropy is, I don't care. You can pick any curve you want. You can go as crazy as you like. As long as you start with the I point, the point I, and then you end at point F, whatever curve you try to calculate the heat over temperature, you will get the exact same delta S, the change of the entropy. Wow. Okay, let's look at the questions. So volume increase, more probability which gas particle can move, arrange itself with, yes, you can, that is the spirit of that thing. Yes, you have more ways that particles, molecules, atoms can, move around, all this stuff. Yes, okay. All right, guys, so that is good. But then when you're Ajahn, wait a second. So if you really want to calculate this, you have to calculate the whole change, right? This expression is just an infinitesimally change. Okay, no big deal. All I have to do is just integrate this equation, and then you get to the final conclusion over here. Ajahn, are you serious about calculus? No. So we're not going to try to do much about calculation, but I hope you see how this goes. Okay, at least you know that the parameters or the quantity that you need for the entropy calculation is the ratio between the heat over temperature, and then you sum those up. And a crucial thing is, if you have a cyclic process, and that's guaranteed the reversibility of that process, that means the entropy change going to be 0 all the time. Of course, because you start and end at the same point, there won't be any entropy change. But that give sort of like based on everything based on, you can see now, the reversibility. And because we use PV diagram for process that we have been studying so far, so this is a reversible process. So you can go from 1 to 2, 2 to 3, 3 to 4, back to 1. So you guarantee that for the whole thing, entropy change is 0. Okay, sounds good. All right. And now, if you're wondering, okay, there's a question comes in. What does a circle here means? And you will face this one more time toward the end of the course. This circle inside or on top of this integral sign is just saying that you're doing in a full circle. So this is just to represent that it's cyclic. You do complete round, complete loop, or any complete something that you come back to the original position. Okay. All right.
Okay.
Okay, but now you probably start to think, Majan, wait a second. We have been studying the first law for like 6 lectures, and you're going to do this entropy just only have a lecture? Answer is yes, but I'm not going to spend so much asking you, sort of like so much time asking you this question in the exam. I probably have only like single question about the entropy. That's it. All right, just to check that you sort of like look into it a little bit, and then I think I'm done. All right, so don't worry about this one, because entropy, it will take weeks to study if you really want to get into it. All right, but you will have a chance to look at some exercises and things that I'm going to post for you guys, and then just try it, and then I think that's very good. All right, and let's see how the calculation is going to be. So let's start with this again, guys. This is going to be like wow. I don't know, to me, to you, I don't know. All right, so start with this. You have seen this before. This is going to be your 3rd time seeing this. It's a free expansion. Remember this container, insulated, no heat allowed to exchange, no heat in, no heat out. The gas started at the bottom half of the container. There's a membrane trying to block it, and then eventually membrane just somehow expired, breaks, whatever reason, and then gas fill up the whole space in the container. So the volume of the gas increased into twice as big. Everyone knows the pressure will be half. So if you start with the pressure like P naught, this one is going to be P naught over 2, because PV equal to nRT all the time. Temperature will not change, same T. Cool. So everyone fine. That's from the first law of thermodynamics. No change. Temperature, no change. No heat flow. No work done. Nothing. This is a free expansion. And now you start to see why we need something more. Because if you don't define the entropy, there's no way for you to tell that, hey, Ajahn, that there are some changes here. The pressure different, volume is different, it's changing. So if we don't have any other quantity to describe this change, then we're going to be kind of like in the dark. So entropy will come into play. Okay, got the idea?
Okay.
There's a question coming. Is this what happened in my Pepsi bottle? When you open it, is that what you're trying to do? If you open it, that is just a outgas of the carbon dioxide that's dissolved in the Pepsi or Coke, whatever brand you prefer. So it's not a free expansion per se, because that one is just because in the pressurized bottle, the carbon dioxide can dissolve in the liquid. But once you open it up, you get back to the room atmosphere. So at 1 atm, the carbon dioxide cannot dissolve in that liquid anymore. So that's why it starts to escape from the liquid. Yeah, so it's not the same, because this one, you need to contain everything inside a closed insulated container. But for the open up a bottle of soda cans, that's already you open up things to the environment. So you're not containing anything. That makes sense. All right. All right. On top of that, of course, it's not ideal gas, but well, we can treat it as an ideal gas. It's not that bad. Yeah. The error is going to be pretty small. All right. But it's just different process. That one is just free expansion to atmospheric pressure. But as you can see, the volume is not fixed because you sort of let it go. Okay. All right. So come back to this. So you start seeing the reason why we need entropy, because something is changing here. Even though energy is not changing, but something is changing. So here we go, guys. Let's calculate delta S. And this is going to be the last exercise for our first module right here. All right. So that's we have arrived at the end of the first module. This is going to be the last topic that we're going to discuss for the thermodynamics. All right, almost there. All right. So, guys, how can we calculate the change of the entropy? But Ajahn, that's not bad because you know where you start. So let me pull up a PV diagram. I'm going to go sort of like through this process together with you guys. So let's say initially you have the pressure P naught and V, it's V in that figure. So let's say you are here. V is right here. Let's say P naught is up here. So let's say that is your starting point right there. Let me call this point number 1. So this is your state number 1. And the final state, your volume is twice as big. The pressure is reduced in half. So that is going to be your final point right there. So you know the state of the gas. Question. What kind of process do you think is happening from 1 to 2? If you want to connecting the dot number 1 and the dots number 2, what do you think, what kind of shape of the curve that you're going to use to describe this free expansion process? Isothermal, very good, very good. So that means I'm gonna connect these two with an isothermal. Why? My question is why? You probably say, but because they are at the same temperature at all times. So we know that these 2 points must be on the same isotherm. Guarantee. Oh, that's not nice. Okay, let's make sure it's on. Guys, correct? So that is very good.
Okay.
Is that the only choice that you can do? The answer is you have actually you have infinitely many curves that you can draw because the delta S is path independent. Okay, so that means you can do this and this if you want. You can do this and this if you like. Or you can just go straight like this if you want. Doesn't matter. You can pick any curves connecting 1 to 2. You will gain the same delta S. You guys with me now? This is pretty much the core concepts of the path independent variable. But the choice that your friends made, that was very good. The reason that we would like to use the isothermal process because it's so simple to calculate. Why pick some other crazy path when this path is so good? T is constant. Okay, so that's how things is going to happen. It's just like, okay, Ajahn, I'm gonna connect them 1 to 2. But now my extra question is, does this gas really follow this path, the isothermal process? No. And I don't even know because this free expansion, I don't think you can drag any, or you cannot draw any line connecting between point 1 and point 2 at all, because is a is a so during that I mean, how can you measure the pressure of the whole container? Because once this, at the moment of the breaking of the membrane, some gas will start to flow in. But of course, you can see some portion of this one still has no molecules of this gas whatsoever. So it's an uneven distribution of the molecules. So you won't be able to measure the pressure for the whole thing. You don't even know how to measure it because you don't know where to put your sensor on. So that VU system is just like, I don't know. So that's what I'm trying to give you a conclusion is. So now conclusion is, if you want to call this an initial state of the gas, this is your final state of the gas. You only know 2 points. But the point in between, actually, you don't need to know because it's unclear, right? It's unclear because you cannot probably keep track of that. But entropy doesn't care. It's path independent. So you can just draw a path yourself and do the calculation right away. Okay, let's do it, guys. So once you connect these 2 dots, and because you clever picking the isothermal process, you know how to calculate everything on here. Let's start from something that we already know. Along this path, delta U is 0. Yes, no temperature change. Along this path, Q must be equal to W. And we already learned that is area under the curve is nRT log of V final over V initial. Yes, very good. But then what we want for this is entropy. Okay, so let's start over one more time, shall we? So let's write everything down in the differential form first, just like we were trying to calculate something. And then we arrive at this nRT over V dV. Everyone checks with this. All right, back in the day of this one, you just integrate this and then you get this value, correct? But at this point, no, wait. We don't want this. What I'm trying to show you is this. I'm just going to divide this through by T. You guys with me? The reason I can do that because this heat came from the isothermal line. So this is going to be my reversible heat. This is Q reversible. Perfect. So once I divide it by the temperature, that is my change of the entropy. A tiny change. Okay?
Okay.
And I want the whole change. I just do the integral of this everywhere. So that means the difference that we are making is just you just divide it by the temperature first before doing the integration. That's all. But the good thing about picking the isothermal process is T is already constant. I can pretty much pull out or cancel out the T. So I only got NR as a constant, but whatever I have left to integrate is still log of the V. So I'm still getting a V final over V initial anyway. Then here is the wow moments, guys. Because the final volume is twice as big, the final ratio here is 2. Can you see this? The delta S is positive. See, isn't that cool? Wow. First law of thermodynamics doesn't give you anything because first state and the final states sharing the same energy, no energy change. But once you look into the entropy change, well, hey, Dan, entropy increases. And you can guess the reason it increases because as we discussed at the starting point of the entropy introduction, the volume increases. The gas can go crazier, you have more place to travel. So if you speak in terms of the disorderness, it's getting more crazy. Gas can go larger volumes, so I can keep track of them more difficult somehow. So that's come into the entropy increases in this system. All right. Got that one? So this is more than just first law. You need the second law too to say, hey, what is going on? Here comes the main character of this. Why do we care so much about the delta S? Because the second law of thermodynamics says, here is the key, guys. Let's jump right into the final conclusion. Okay. The change in entropy must be greater than 0, positive change, for bam, 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 irreversible process. And somehow, if you get to a system that have 0 change, that means you are dealing with a reversible process. And look at this, what you got. You get a positive change in entropy. So that means this free expansion of the gas is an irreversible process. That's what it is.
Okay.
And even more to it, for those of you that doing computer science, computer engineer people, this number 2 right here has the meaning, believe it or not. Because this number 2 is actually give you a sense of this difference of a system. Right here, you can think of it, or you can think of it, you can look at the vacuum in the upper half of this container. This can represent like a 0 state. This can represent like a 1 state. It's a 0 and 1 because these are definitely 2 different states of the system. And that means this is like a 1-bit system. It's 2 to the 1. So you have 2 choices, yes or no, 0 and 1, but then you only have these 2 choices. So actually the numbers that come in the end over here can give you the magnitude of the information that this system can hold. Wow. Wow. All right. So this is eventually going to be data science or computer science, computer engineering in the future. And in the era that we are dealing with so much with like a big data, there must be a way that you can quantify amount of data in the world or whatever in the universe and things like that. And it turns out the entropy will have a direct connections to the data, amount of data, or I would say amount of information that can store in one particular system. You use definition of entropy for that. Okay, sounds cool. All right, I think that is very cool. Wow. Eventually, that's the second law of thermodynamics give you connections to the data science at the fundamental levels, turns out. All right, and this give you an idea that from now on, if you have a cup of hot water or cold water, you put it on the table, have it sit there, you know that the process is going to be irreversible because the hot coffee will get colder down to room temperature. It's not going to get hot by itself. If you try to calculate the entropy change of that hot coffee, it's going to give you a positive change because it's representing an irreversible process. Okay, so the best thing that you can do in this universe is keep entropy unchanged. That's the best you can do. You cannot reverse things. You cannot reduce your entropy. Even though you might say about Ajahn, actually in some particular state or in some particular scenario, the entropy change is negative. It's possible, but don't forget you have to take into account the whole universe. You can think of the universe as a real universe or a universe in terms of the thermodynamics. It's just system plus environment. No matter what you do, if you take into account the change of the entropy everywhere in the universe, the best that it can do is 0 change. There won't be any negative change for the whole universe. So that's why that is like the crazy counterintuitive stuff that we sort of like cannot get understanding down to the bottom of this so much, because entropy always increased, guys. Right now.
Again,
Yes.
question.
Yeah.
What if the space is limited? I mean, like the volume is finitely small, can the entropy increase?
Come again.
What if I keep shrinking the universe? Can the entropy still increase?
Okay. Maybe. Okay. All right. I'll explain this to the rest of you guys too. So the idea is this. Right now, we know that our universe is actually expanding, but we don't actually know much about what is going on. If at the end of it, we're going to shrink back down again. So you guys probably heard of Big Bang, but then there are theories talking about at the end of it, the gravity will pull everything back, and then you're gonna have like a big crunch or something. And this whole process might be like oscillations, like bang and then crunch back and then bang again. But we just don't live long enough to see the whole thing, right? But at this moment right now, the universe is expanding. So you guys are witnessing the increase in the entropy phase of the universe. Think of it that way. You're probably not going to live long enough to be at the moment that the entropy is at the time that is reducing. So don't worry about that yet. Okay, but at this point, this is the reason why you are getting older. You guys are aging. Why things are getting more disorder. You buying stuff. Okay, one example that I always give you an idea is when you buy a new deck of cards, it came in perfect order. Yeah, ace, 2, 3, 4, 5, kings or whatever, and it's already ordered in suit and everything perfect. But once you play cards, you shuffle them. See, you never ever get that order back. That is an almost impossible. You can keep shuffling until you, I don't know, until you give it to your sons. You you can keep shuffling for the rest of your life. You're never gonna have them back in order again. So that's a kind of process that is irreversible. So anything that is irreversible, and then when you try to look at the entropy of it, the entropy will always increase. You guys getting older, your cells is disintegrated, so that's why it's dissipating out. And here comes I think my grand conclusion is this. When you use the word disorder, sometimes it doesn't make sense, because when you are aging, why you say you are more disorder, you might be able to say, okay, disorder means my organs, my stuff doesn't really function as well as before. That probably possible. But what I'm saying is actually the entropy increase. It means universe is trying to get to a uniformity. Everything's supposed to distribute out until there's nothing else to distribute anymore. That's what it's, to me, that's what it really means by entropy. So when you guys are getting older, you aging, because eventually you're gonna die, and then you sit in, well, don't have, I mean, you're probably in the coffin somewhere. But anyway, so the thing is, we're gonna dissipate, we're gonna like disintegrate everything, and then we down to the ground. We get nothing left. That's uniform with the with the nature. That's what it is. Why hot meet with the cold? Why they have to transfer? Because eventually they want to balance everything until there's nothing to transfer. So actually, I don't know, you call this more disorder or more order, I don't know, but at least that's what it means, is more uniform. So that's why our universe is trying to expand, because everything is supposed to eventually die, and the universe will have every point in space with no stars, nothing at all. It will be like a perfect uniform space. And that's when everything stopped changing. And that's when the end of the entropy change. Yes.
Question. Again, why life exists? Because life requires order.
That I don't know. I'm not so sure. That is still, I think that is still uh, 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 I don't know, it's like questionable thing to ask. We don't even know where we were, where were we, how we are, how we born. That I don't know. It's still weird. We still have cell phone to use. Why we have this? Why we have Earth? We have life. That is more complicated than that. But at
เมื่อ
least
กี้ particle right that order can form from big order
right.
and
That's still tough.
partibility
That's still tough. But to me, if I were to answer your question, well, we are not an order stuff. What we are just a flash of an event in the universe. That's my answer. So think in the time scale of the universe, the life of the earth is like, it's not even a blink. It's a fraction of a fraction of a fraction of a blink. So what we are doing here is just like a non-uniformity of the universe that just come up and then just maybe just disappear. Who knows? From the scale of time of the universe. So what we seems like we are in order right now, it's just universe is balancing itself out. So during that balancing act at the at some point, there will be some overshoot, there will be undershoot. So we are just probably somewhere up or down, above the average, below the average somehow. But at the end of the universe, everything's supposed to be, there you go, uniform. And that is the heat death of the universe. At that point, at the end of time, there will be no more heat, because the temperature everywhere in the universe will be all uniform, same temperature, no more energy flow. And that's the conclusion of this part. Is it good? So as you can see, toward the end, I don't want to put much of the calculations and everything. So the only thing that you need to probably go back and maybe put your effort into calculations a little bit is just looking at a couple of exercises in entropy calculation. That's it. All right. Don't worry too much about integrations or calculus. It's going to be like, I think maybe a very simple integral, something like that. Sounds good, guys. And congratulations to maybe to me, to you, that we already done with the first module right here. Okay. Any questions? Thermodynamics question first, I think, at this point. My knowledge is lost in entropy. Wow, that's true. Maybe the reason that you cannot remember everything because, yeah, the brain is working at, yeah, you have to maintain your memory somehow. If you're not using it much, it's dissipate in time. So that's, I think that's part of the second law of thermodynamics. I think everything is nature's law, so you cannot go against it. Yes. Can delta U be negative? A little confused with the question in the homework. Yes, delta U can be negative. For example, when the temperature of the gas is reduced, then definitely delta U is negative. Yes, it's possible. Yep. Already. Okay, so let's discuss about our exam, shall we? All right, so you guys, seems like you picked Sunday, Saturday, and Sunday, right? Although there are a couple of you guys seems like maybe need some extra arrangement. I think I can do it, so don't worry about that. So that should be fine. Now here comes the question: do you want to have exam this coming week or the week after? Maybe this coming week is too soon, I guess. I don't know. You haven't had time to study yet. So we can have the midterm, not the midterm, it's the first exam on 17th if you want. That was the pain. Yeah, week after. That makes sense. Oh yeah, definitely. Okay, so I'm going for it. That's actually my proposal. Because I think you need time to digest and stuff. It doesn't make sense me to teach you now and then take the exam like this Sunday. That doesn't make sense. Okay. And that's part of the reason. That's why if you looked at the due date on the exercise, I put it at October 10th or something like that. Because beyond that date, I will post the solution. Well, it's not a solution per se. It's going to be like an answer to those problems. Sounds good? All right. Oh yeah, you got genetic, bio, I know. All right. So I'll just free form. So for physics, just any time slot that you want to squeeze in. So Okay, so yeah, we will have a review session. Sounds good? Yes. So what I'm gonna plan to do is this, guys. Okay, so if okay, let's stick with this plan. So I'm gonna have the exam on 17 Sunday. 17. So that's Sunday. But for those of you, some of you that couldn't do this one, that's fine. I can do special arrangement. You can start at different time or different dates. That's no big deal. But then on the Saturday 16, shall we meet to do the review for this thermodynamics module? Sounds like a good plan. Okay. Which time slot? Yeah, we can pick like maybe in the morning, Saturday morning. Yeah, sounds good. Maybe like I can show up like 9 a.m. Or let's do 10 to 12, something like 10 to 12 on October 16th. Sounds like a good plan. Yeah, we'll do the recording for sure. Just for those of you that couldn't make it to class, they'll be the recording. And then if you have other times in the afternoon or whatever before the exam, then you have a chance to do it. All right. And I'm going to release the exam because it's a take-home exam. So it's going to release, let's say, right 8 a.m. on Saturday. Okay. And then you have 12 hours to do it. So you just hand it in 8 p.m. All right. And for those of you that couldn't make it on Sunday, if you really stuck or cannot do, that's fine. You're going to have the same 12 hours time period. All right. So we can do like you can contact me personally and then we can set up date and time for you to do the homework. Sounds like flexible enough for everyone. Yeah, this exam cover everything up to today. Correct. So the first exam will be all about thermodynamics up to this slide handouts right away. Yep. Will there be a makeup class for the class that we cancel? I don't think we need to make, let's think of that makeup class to be our Q&A. Sounds like a good one. So we don't have to push too much work into it. So let's think of the makeup class to be the review. That was the review session for us. I think that sounds good. Wait, I'm confused. Can you repeat the date and time for the exam again? In conclusion. Okay, one more time. So on Sunday, we have a Q&A sessions. So you guys can ask, or I can show you how things done for the homework or give you a solution and all the stuff all together. That will be on Saturday 16 in the morning, 10 to 12. Okay. And then the exam will be on Sunday. Okay. Sounds good. On Sunday, 17th. Yeah. Okay. All right. And you have 12 hours to complete your homework. Not homework, is a exam. Practice exam. Not a promise, but I think I can come up with one. I think I can just sort of like collect more exercises and then put them up into like a mock exam, something like that, right? So I can prepare a mock-up. Yeah, but definitely it's going to be similar to the homework. Yes. So the question in the exam will be similar to the homework, the question that we did in class, in the handouts, on and on. Yeah, 8 to 8, correct. 8 a.m. to 8 p.m. Yeah, 12 hours total. Sounds like a good plan. Okay. Yeah. Okay. Everyone sounds cool plan. Okay, that's good. All right. And then I think we're gonna run something like this. So next week we still study. We'll keep going. So we're gonna keep rolling, move on to waves and optics and other stuff. But then we're gonna have exam the next Sunday. Sounds good. All right. So everyone agree, and I think that's good because this is not gonna overlap with the rest of other subjects. So we flying higher. Physics is flying higher. All right. Okay. All right, guys. Thank you so much for today's, and really sorry about the delay. All right, but I think we got everything in time, so that's good. Thank you. All right. Thank you very much. And of course, don't forget to try the homework, and then I'll check out if I can do the mock exam for you guys, so you have extra practice exercises. But don't go crazy. You don't have to like try all the problems in the textbook, and my exam won't be that bad at all. You will be surprised how easy it is. All right, so stick with the exercises and some examples that very close to what we did in class. I think that's more than enough. All right, just make sure that you understand things and then just practice just enough. I think that you should be fine. But if not, then we have 2 more exam to try. So first exam, sort of like give it a shot and see how it goes. All right, sounds good. All right, so Jim Renner, StarCraft. Sounds like a plan. Okay, all right, cool, guys. So take care of each other, take care of yourself, and then I'll see you guys on Monday. Yeah. All right, guys. Bye bye.
Bye, Chan.
Thank you. Yep.